Imagine you're holding a balloon. It slips from your fingers, rises gently, and disappears into the sky. It feels like nothing, just a small, harmless moment. But what if I told you that in that exact moment, something irreplaceable left our planet forever? Not metaphorically, literally, gone beyond recovery, drifting into space, never to return. Now here's the strange part. This isn't some rare accident. It's happening all the time, quietly, invisibly, while most of us don't even think twice about it. And the substance we're losing isn't just for balloons or party tricks. It's something that hospitals depend on to see inside the human body. It's something scientists rely on to unlock the deepest secrets of the universe. It's something that makes modern technology possible in ways you've probably never imagined. So the real question isn't what is helium? The real question is, how did something so critical become something we treat as disposable? And even more unsettling, what happens when it's no longer there? Because this isn't a story about the future. It's already happening. And once you see the full picture, you won't look at something as simple as a floating balloon the same way again. Imagine holding something in your hand that looks trivial, feels light, and disappears without a trace, yet silently supports some of the most advanced achievements of human civilization. That substance is helium. Not dramatic, not loud, not even visible in most cases, and yet its absence would ripple through science, medicine, and technology in ways that most people have never even considered. To understand what happens when helium vanishes, you have to begin with a simple but unsettling truth. Helium is not something we can just make more of whenever we feel like it. Deep beneath your feet, inside the Earth's crust, radioactive elements like uranium and thorium slowly decay. In that process, they emit tiny particles called alpha particles, which are essentially the nuclei of helium atoms. Over millions of years, these particles capture electrons and become helium gas. It seeps through rock, sometimes getting trapped in underground pockets along with natural gas. That's where most of the helium we use comes from. But here's the catch. This process takes geological time, millions, even billions of years for meaningful accumulation. When we extract helium and release it into the atmosphere, it doesn't stay around. Being incredibly light, it rises, escapes Earth's gravitational grip, and drifts off into space forever. Gone. Not recycled, not recoverable. So every balloon that floats away isn't just a fleeting decoration. It's a tiny piece of a resource permanently lost from the planet. You start to realize this isn't just a supply problem, it's a one-way leak. Now you might think, fine, so it's rare, but how important can it really be? That's where things get interesting. Helium isn't just another industrial gas sitting in a catalog. It occupies a very strange corner of physics. It refuses to behave like most substances. Cool it down enough, and instead of freezing like everything else, helium remains liquid at temperatures close to absolute zero unless you apply pressure. That alone is bizarre, but it gets better. In that ultra-cold liquid state, helium exhibits quantum mechanical behavior on a macroscopic scale. It can flow without viscosity, climb the walls of containers, and do things that feel almost like magic if you're not used to thinking in terms of quantum physics. These properties are not just curiosities. They are the backbone of some of our most powerful technologies. Take medical imaging, for example. Inside hospitals around the world, MRI machines rely on extremely strong magnetic fields to peer inside the human body without surgery. Those magnets are made of superconducting materials, which only work when cooled to incredibly low temperatures. And what do we use to reach those temperatures? Liquid helium. Without it, the magnets lose their superconductivity, the machines stop working, and a critical diagnostic tool disappears. This isn't some luxury device used occasionally. It's a cornerstone of modern medicine. Thousands of diagnoses every day depend on it. If helium becomes scarce or disappears, hospitals don't just face inconvenience, they face a fundamental loss of capability. And it's not just medicine. In laboratories, scientists use helium to cool particle detectors, to maintain stable environments for experiments, and to explore the frontiers of physics. The very experiments that try to understand the universe at its deepest level depend on helium's ability to reach temperatures that nothing else can easily achieve. Remove helium, and you're not just turning off machines, you're dimming humanity's ability to ask certain kinds of questions about reality itself. Then there's the illusion that helium is abundant. After all, it's everywhere at birthday parties, floating above children's heads in bright, colorful balloons. That image creates a psychological trap. If something is used so casually, it must be plentiful. But that's not how reality works. The helium in those balloons often comes from the same reserves that supply hospitals and research facilities. Extracting helium is not straightforward. It's usually a byproduct of natural gas production, and only certain gas fields contain significant amounts of it. Once those fields are depleted, that source is gone. There's no factory somewhere churning out helium from raw materials in a scalable way. What we have is what nature prepared over unimaginable stretches of time. So we live in a strange contradiction. On one hand, helium is treated like a toy. On the other, it is a critical component of systems that define modern civilization. That mismatch between perception and reality leads to careless use. When prices drop or supply seems stable, consumption increases, especially in non-essential applications. But when shortages hit, and they have, multiple times, the consequences are immediate and serious. Research labs shut down experiments because they can't maintain low temperatures. Hospitals delay maintenance or upgrades to imaging equipment. Industries that rely on helium for leak detection, semiconductor manufacturing, or fiber optics face disruptions. It's a quiet crisis because it doesn't explode or make headlines in the same way as oil shortages, but its effects are deeply embedded in the infrastructure of science and technology. If you follow this chain of dependence far enough, you begin to see how interconnected everything is. Space exploration, for instance, uses helium to pressurize fuel tanks in rockets. Without it, launches become more complicated, more expensive, or even unfeasible with current designs. In electronics, helium is used in manufacturing processes that produce the chips powering your phone, your computer, and the global internet infrastructure. Remove helium, and suddenly progress in computing slows down, not because we lack ideas, but because we lack the means to implement them efficiently. What makes the situation even more fascinating is that helium's uniqueness isn't just about being cold or inert. It's about being irreplaceable in certain roles. You can substitute materials in many engineering problems. If copper becomes expensive, you find alternatives. If a particular fuel runs out, you develop another energy source. But helium sits in a niche where its combination of properties, extreme lightness, chemical inertness, and unmatched cryogenic capability, makes substitution extremely difficult. There are alternatives in some cases, but they are often less efficient, more expensive, or technically challenging to implement at scale. So losing helium doesn't just mean switching to something else easily. It often means accepting limitations. Now imagine for a moment a world where helium has effectively vanished from Earth's usable supply. The change wouldn't come as a dramatic overnight collapse. It would be gradual, almost subtle at first. Prices would rise. Industries would prioritize essential uses. Balloons would disappear first, not because of regulation necessarily, but because they would become economically unjustifiable. Then research facilities would start to feel the squeeze. Experiments would be delayed, redesigned, or abandoned. Medical institutions would ration usage, focusing on the most critical cases. The ripple effects would spread outward, touching areas you wouldn't immediately connect to a simple gas. And here's the deeper lesson hiding beneath all of this. It's not really about helium alone. It's about how we interact with the hidden foundations of our world. So many of the things that make modern life possible are invisible to us. We don't think about them because they work quietly in the background. Electricity flows, data moves, machines operate, and we assume it will always be that way. But systems are often more fragile than they appear, especially when they depend on resources that cannot be easily replaced. Helium is a perfect example of this hidden fragility. It teaches you that rarity is not always obvious, that importance is not always visible, and that the smallest, lightest things can carry enormous weight in the structure of civilization. When you lose something like helium, you're not just losing a gas. You're losing a set of possibilities. Certain experiments can no longer be done in the same way. Certain technologies become harder to maintain. Certain paths of progress narrow or disappear entirely. And perhaps the most striking part is how avoidable some of the consequences could be with awareness and careful management. Conservation, recycling systems, better allocation of resources. These are not exotic solutions. They are practical steps, but they require a shift in perspective. from seeing helium as trivial to recognizing it as a finite and valuable component of our technological ecosystem. So when you think about helium vanishing from Earth, don't picture just empty party stores or silent balloons drifting away. Picture MRI machines struggling to operate, research labs pausing at the edge of discovery, rockets grounded, and the slow, quiet dimming of certain kinds of human progress. The shock isn't in the disappearance itself. It's in realizing how something so small, so easily overlooked, has been holding up so much of what we take for granted. And so, after following this quiet trail from deep inside the Earth to the edge of space, you begin to see the pattern. The story was never really about helium alone. It was about how something so small, so invisible, can sit at the center of systems we depend on without ever demanding our attention. Until, of course, it's gone. What makes this realization powerful is not fear, it's awareness. Because once you understand that certain resources don't come back, that some losses are permanent, your perspective changes. You start to see value where you once saw simplicity. You begin to question what else we might be overlooking, what other silent pillars are holding up the world we take for granted. The disappearance of helium wouldn't arrive with a loud warning. It would come quietly, step by step, through limitations, delays, and missed opportunities, until one day we realize that progress itself has slowed in ways we didn't expect. And by then, the real question won't be what happened. It will be, why didn't we see it sooner? But here's the hopeful part. Understanding changes outcomes. The moment you recognize the importance of something, you gain the power to treat it differently, to think more carefully, to act more responsibly. And that shift, small as it may seem, is how larger changes begin. So as you walk away from this idea, carry one simple thought with you. The most important things in our world are often the ones we notice the least. And once you start noticing them, you start seeing the world in a completely different way. Good luck on your journey of curiosity and discovery. Keep questioning, keep exploring, and never stop looking deeper than what's obvious. Thank you.